Hello, my name is Volodymyr. I am engineer at EPAM Systems. Artem Migaev already told you about what we are doing at EPAM, about automotive vendors and so on. So I don't want to repeat all this. Most of the modern ARM BSPs include trusted execution environment of some sort, and it is naturally to want to share this TEE between different virtual machines. And this is the topic of my talk today. So here's the agenda. At first, I want to give you some background about what is TE and why it can be needed. Then I will talk about OpTE and how I implemented virtualization support in it. And then I will switch to Zen and tell you about OpTE Mediator in Zen. So TE, or trusted execution environment, is a very small minimalistic OS that is designed to run special trusted applications, or TAs. There is an organization named Global Platform that develops specifications for TEs. Those specs include basic requirements, APIs, and so on and so on. So yeah. Why do we need this TE at all? It is intended to run some highly secured applications like embedded SIEMs. I believe they can be found in newest Google and Apple phones. They also can be used for contactless payments like Google Pay. Some cryptographic services like key storage, key management, message signing, and so on and so on. Also, I know about a couple of DRM implementations that were done in TE. Probably there are some other uses. So this is a very simplified diagram on how TE interacts with your platform. Rich execution environment is another term that was created by Global Platform. This is basically your OS like Linux or Windows, FreeBSD, whatever. So what we have here is TE on the right side and our normal OS. They should be isolated from each other, but global platform does not specify how it can be done. For example, you can run TE on a completely different chip and it will be okay. But on ARM platform, we have ARM trusted zone that enables us a completely secure mode for CPU. Also, it adds secured memory, secured interrupts, secured timers, and so on and so on. And we can run TE in this ARM-TZ. So basically, this is how it is working. We have client application that is running in your OS, and when it wants to get some services from TA, it calls kernel driver in, say, Linux. This kernel driver issues SMC call that is handled by OpTE in our case, and then OpTE calls your trusted application. Yeah. So about OPTE. OPTE is the open source implementation for global platform specifications for ARM platforms. Initially, it was created by ST Ericsson as closed sources, but it was open in 2013. Right now, it is maintained and developed mostly by Linaro, but there are other contributors as well. Upstream branch of PE supports many different platforms, and I believe that in-house branches support even more. PE implements global platform specifications, and it even tests passes tests provided by global platform. And for last two releases, OPTE have utilization support. I want to share some details how I added the support to OPTE, because main problem is that initially OPTE was not designed to have utilization support. It thinks that there is only one client OS, and it is, how to say, embedded deeply into the code base. So it's as any other kernel or OS stores state in global variables, uses heap, and so on. Wow. But luckily for us, we can divide OPTE code into two big parts. One part we called Nexus. This is basically a very kernel of OPTE. It includes low-level code like exception handling, entry and exit to OPTE, MU management, drivers, and such other stuff. And another part, provides real value to OPTE. It capable of handling this application. It knows about threads, mutexes. It implements global platform APIs, and so on, so on. So basically, if you want to add support for utilization into OPTE, we want to have one Nexus instance and multiple TE instances, one instance per guest. There is an obvious way how we can do this. We can create some structure like VM context and store all data that belongs to TE in that structure. And then we can either pass this structure to any of the functions that uses TE, or implement some sort of current variable, like in Zen or Linux. This is obvious approach. It have its own pros and cons. It is very simple to understand, but I tried to implement this solution, and I got stuck because basically OPTE is not created for this sort of changes, and I need to rewrite from scratch big parts of TE. So it is not very good way. So then I chose another approach. Actually, we can move all global state of a TE kernel into open sections in memory, and then we can have multiple sections for each of virtual machine state. And then when we receiving call from some VM, we can map sections for that virtual machine into TE address space, and basically that's all. This have own benefits like isolation, because in this time, in this case, only one state for one guest is mapped into OPT address space for each PCPU. So even if is there some bug or security issue in OPT, it can't access data for other guests. Another big feature that we don't need to do any changes to the biggest part of TE, which is handless global platform specifications. All what we need to do is alter MMU code, add the hooks to enter and exit paths, so we can map and map states for needed guest, and then move some variables to the next sections. And downside is that it is quite unusual and is harder to understand. But anyways, this approach was merged into TE, and it is approach working. But it is good to have support in TE, but we need some support from normal space also. At first, we need to inform OPT about guest lifecycle. Basically, we need to tell OPT when a guest is being created or when guest is dies, so we can free all resources for that guest. Then there can be number of different TEs, and we need to tell guests which TE is present on the platform. Then we need to control access, because we don't need all guests to work with TE. Another problem is shared memory, because guests doesn't know real physical addresses of own memory, and OPT on other hand does not know nothing about intermediate addresses. So we need to translate them. About shared memory, we also need to pin shared pages to make sure that guests will not balloon out that memory. So this is how it can look like when we have a mediator in Xen. Now all calls are handled by mediator, and mediator in turn calls real OPT. At first I created a very small framework for TE mediators. It is really very simple. All it can do, it can probe for OPT on the platform to check what is really present on your machine. Then it have hooks for domain creation and destruction. And of course, it handles calls from guest to TE. So I wrote mediator for OPT in Xen. At this time, it is functional. OPT passes all internal tests, but it is still in experimental state, because there are some security considerations in Xen. So this is a basic flow of a mediator. It looks like very simple. All we need to do is receive a request from guest, check what is the request, then change arguments, for example, do some memory translation, and then we need to call real optee if you don't want to, then check return values and return results back to the guest. But there was a couple of challenges in this mediator. For example, first problem is that we have two types of call to optee. One call is call it fast call. It is really fast because it is not intended to block in TE. It is used for simple things like housekeeping. For example, here is this call on the left. For example, we can get version, that's all. But there is another type of the call to optee, which is called the standard call. Logically, this is one call to optee, but it can be preempted by normal world, and so it can be like a series of invocations of optee in the context of one call. This call can be interrupted by things like interrupt request to normal world. This call can be blocked because we have some mutex or something like that. And also optee can break this call because it wants some services from your OS. For example, it wants to read or write a file, send some network packet, and so on. So again, example of a standard call is on the right. As you can see, this is like one logical call, but it consists of series of SMC calls to the optee. And then, for example, optee wants us to allocate some shared buffer, or optee asks us to handle interrupt, or something like that. So this leads to a problem when we need to track state of this call in the optee mediator. And because there's a series of SMC calls, there can be some tricky situations when, for example, guest dies in the middle of the call, or guest dies something strange with open shared memory, and we can't continue the call, and we need to terminate it for both the optee and for the guest. It leads to somewhat complex logic. Another challenge is shared memory, because the global platform requires that we can share memory between client application in normal world and between trusted application in optee. How it is done? Guest sends a scatter list of intermediate physical address to optee, and we need optee mediator to do translation. And then we need to pin those pages to make sure that they will not disappear when optee uses them. This also can be tricky because there are a number of different types of shared memory, and we need to track all of them. and we need to be sure that it all will be freed when guest is being destroyed. So yes, so there's also some complex logic in this part of Mediator. Yeah, so about current status, for OPT, we have merged support in OPT 3.5. Part of the patches are merged to the Xen hypervisor, but there are still patches for toolstack under review. So right now only DOM0 can talk to OPT because tools know nothing about OPT and can't create new guests with support. Yeah, and those, okay, so the feature plans for OPT. We have basic support for visualization, but right now we can't access real hardware because we don't know how to share this hardware between different guests. So right now this support is completely disabled, but we want to add it in the future. So there is two big parts of this. This is cryptographic hardware accelerators. We need some way to share this, but I don't think that it will be very hard. And another problem is secure storage on some external hardware. And in this case, we need to do some partitioning. So OPT can use parts of the storage for one guest and parts for the other guest. And also we need some way to authenticate guests before they can access this storage. This is not done, and it is like being designed right now. So yeah, and plans for them right now. Mediator is in experimental state, so it is not ready for production. We need to do a couple of things before we can make it more mature. First, we need to limit number of P2M lookups because right now, in the worst case, Mediator can do up to 16,000 lookups per one call to OPT, which is not good. Then we need some way to limit the heap memory usage because OPT Mediator creates a number of different structures to share, to handle and direct shared memory. Then we need to handle machine device tree because right now Mediator just leaves it as it is and doesn't change information about OPT. And yes, there are some leaky cases in standard call handling which we need to address also. And when we will add support for hardware into OPT, we need to add support for hardware MT in OPT Mediator as well. Yeah, this basically is all. If you have any questions, you can ask them. Yeah. Okay, so thank you.